I have a reasonably resistive wire here that's 1 meter long, and you can see that I've put tape on it every 10 centimeters. If I connect this wire to a 1 volt power supply, electric current begins to flow through this loop. I also have a voltmeter here, so we can check the voltage around the loop of wire. And at the beginning of the loop, it's 1 volt, and then 10 centimeters down, it's 0.9 volts, and then 0.8 volts, and so on, all the way until you get to the other end of the wire where it is 0 volts. If we plot this as a voltage versus length of wire, we can see that it's just making a straight line. But what if I were to take this wire, cut it in the middle, and splice in something to impede the progress of the electrons that are flowing through this wire? Here is one I prepared earlier. This is 2 50 centimeter lengths of the exact same wire, and in between them I have soldered a 100 ohm resistor. This resistor right here really just serves to slow down the electrons that are moving through the loop. But when we do the same experiment and we look at the voltage around the loop, we see something pretty interesting. Over here by the positive side of the power supply, we still see a volt. But as we move around, that's still a volt, that's still a volt, that's still a volt. And then on the other side of the resistor, we see just about 0 volts, 0 volts, 0 volts, all the way back to the power supply. So we have turned this smooth gradient into a step where all of our voltage is being dropped in this one particular spot at this component, rather than, smoothly declining as we go around the loop of wire. If you've read the first few pages of the first chapter of any electrical engineering textbook, this behavior is not going to surprise you. These electrons are obeying Ohm's law. I cannot overstate that Ohm's law is the foundation of electrical engineering. Like, so many ridiculously complicated things eventually boil down to some statement of Ohm's law. But at the end of the day, it's just an equation. It doesn't give us intuition by itself. While Ohm's law does allow you to compute what's going to happen in a situation like this with great accuracy, what's crazy to me is that this just happens. Like, somehow the electrons know what to do. Individual electrons don't know Ohm's law. An electron can't do math, but somehow, every time you connect a circuit like this, as the electrons start their slow trudge around this wire, leaving from this socket and re-entering this socket, they arrange themselves in accordance with this one simple mathematical rule. Why? Ohm's law is one of the most fundamentally useful equations in physics, and it forms the basis of just about all electrical engineering. Also because it's just a crazy simple formula that basically says one thing is proportional to some other thing by some fixed constant, means that there are loads of analogous systems. And nothing exemplifies this more than the so-called hydraulic analogy. It even has its own Wikipedia page. The gist is that electrons flowing through a wire are almost directly analogous to water molecules flowing through a pipe. And if you connect a loop of pipes with a pump on one side and a water wheel on the other side, it's clear that you're transmitting energy from the pump to the wheel using the flow of the water, but any given molecule of water doesn't need to go all the way around the loop to make it happen. There are a lot of great parallels. I like to imagine this slightly differently as water flowing down a narrow channel, as opposed to flowing down an enclosed pipe, because I think that the channel model helps to explain the concept of voltage, which is a doozy. But before I explain how water can completely and perfectly demonstrate Ohm's law and all things having to do with electricity, I need to explain the 3 elements of Ohm's law: potential, current, and resistance. Let's start with I in V equals IR, the current. What is current? Current is a measurement of charge flow per time. Current in a metallic wire is literally measuring the number of electrons that pass by a certain point on that wire in a given time frame. It's measured in units called amps, and an amp is 1 coulomb per second. Since 1 coulomb is the amount of charge carried by 6.2 million electrons, 1 amp is a lot of moving particles. This wire has an amp running through it right now, which means that there are literally 6.2 million electrons being shoved into the wire every second at this end, and 6.2 million electrons being pulled out of the wire every second at this end. Now, if you look at how many mobile electrons are already contained within this wire, which is a lot, that 6.2 million electrons doesn't seem to go as far. The average electron is only moving, scooching forward very slowly through this wire about a millimeter every 4 seconds. That means that if I left this on for a few hours, I would not only risk burning my house down, I would also very slowly replace all of the electrons in this wire with new electrons that came from inside the power supply. But electrons are indistinguishable fundamental particles, so whatever. Now, if I increase the current flowing through this wire, now we have roughly 4 amps flowing through this wire. That means that the average speed of an electron chugging its way around this wire is about 1 millimeter per second. The drift velocity of the electrons, the average speed as they move around the loop, is linearly proportional to the current. And now this is starting to smell and smoke, so I'm turning it off. As these electrons move through the wire, they do so with some friction. That's one of the reasons that they chug along so slowly. It's also why this started to get hot and singe all of these pieces of tape that I had on here a second ago. The classical view of electrical resistance is like a Plinko board, where electrons want to move from one side to the other, but there's stuff in the way, namely atomic nuclei. This Plinko model isn't as good as the water model, but I think it can demonstrate the effect of resistance really well. The slightly more subtle point is that while these electrons are indeed driven from one side to the other by an external force that we'll talk about in a minute, the lattice they collide with is continuously vibrating. With every given collision, an electron may gain kinetic energy or lose kinetic energy. It may be propelled forwards down the wire, or it may be propelled backwards. It's generally just shot away in a random direction after each collision. Only on average does any given electron appear to move down the wire. When I said a minute ago that the average electron speed was only about a millimeter per second, I meant this average speed, including all of the backtracking. At any given instant, if 2 electrons are moving in a wire in opposite directions, but at the same speed, they basically cancel each other out. This is something that a multimeter can't detect. That's why we only talk about averages. And if a multimeter can't tell the difference between 2 electrons that are going in opposite directions or 2 electrons that are just sitting there and standing still, then that means that a motor or an LED or a processor also can't tell the difference between electrons that are moving in opposite directions and electrons that are standing still. That's why we typically ignore all of these little random fluctuations and just talk about electrons drifting slowly through the wire. Because all these little fluctuations, in the most literal meaning of the word, don't work. When we see electrons move into one end of a wire and we see less concentrated electrons move out the other end of the wire, then something in between must have slowed them down. And that thing is termed resistance. And now we get to the really tricky one, voltage. Or to be a little bit more physicsy, electrostatic potential. Now, you may have noticed that I changed shirts again for this segment, and that's because this isn't my first attempt at filming this segment. Voltage is weird. Like, voltage is one of the least intuitive things that you will come across. It took me many analogies spread out over years before I felt like I finally had a grip on what voltage was and how to intuitively work with it. So in this segment, I'm going to try to throw as many analogies as possible out, and hopefully one of them clicks for you. If not, don't worry about it. It's weird. The most common explanation of voltage is that it's like a pressure, an electron pressure. If you've got a wire and you've got pressurized electrons at one end and less pressurized electrons at the other end, there's some sort of force that's shoving electrons through the wire so that they spread out. I'm going to try to explain what that means and how electrons in some part of a wire can get pressurized. But first, let's do an example. Here I have a 2000 ohm resistor, and if I want to flow a particular number of electrons through that resistor every second, as in I want to reach a particular electric current as read by this ammeter, I have to apply a particular voltage. You might think of a 1.5 volt battery or 6 volt battery or 9 volt battery or a 12 volt battery, or all the different sizes of batteries. In this case, let's say that I want 3 milliamps, or about 2 times 10 to the 16 electrons per second flowing through that resistor. If we use Ohm's law, we can multiply 2000 ohms by 0.003 amps and get 6 volts. If I turn the power supply up to 6 volts, we see that about 3 milliamps of current starts to flow. Great! Math works. Now if we want more current, more electrons per second flowing through this resistor, we can sort of push them harder. We can increase the voltage and the current goes up linearly, where resistance is the slope of that line. This is the mathematical meaning of Ohm's law. I think this is a useful example, but I want to be very careful not to imply that voltage is a force. Voltage is not a force. Now, when you have a voltage difference between two ends of a conductor, there is a force that's propelling electrons, pushing electrons from one end of the wire to the other. But that's not voltage, that's the Coulombic force. Voltage is its own thing. It's an electrostatic potential. This is the book that I learned electrostatics from, and the word volt appears on precisely one page as a unit of this thing called electrostatic potential. When you hear the word potential, you might think of the phrase potential energy, and you should. But you have to be a little bit careful because a volt is not a unit of energy. A lot of sources, including this book, get really pedantic about this distinction, but it's not as complicated as they make it seem. Voltage is to electrostatic potential energy the same way that height is to gravitational potential energy. If you take a ball and you roll it up a hill, you have stored gravitational potential energy, mgh. The mass of the ball times the acceleration of gravity times the height of the hill. If you let the ball go and roll back down the hill, that's the amount of kinetic energy it will have as it rolls away. If you take the same ball and you roll it up a hill that's twice as tall, you will have stored twice as much energy in that ball. So while meters, the height of the hill, isn't literally a unit of energy, you can say that the amount of gravitational potential energy that you're storing is directly proportional to how high did you push the ball. Replace the height of the hill with a voltage and replace the ball with an electron, and you're in business. The fun thing is that electrons all have the exact same mass and obey the exact same electrostatic rules that would be akin to the acceleration of gravity going up the hill. This means that if you do want to express an energy, we have this great unit called the electron volt, where we take one electron and we push it up a hill that's exactly 1 volt tall. If you really care, an electron volt is about 1.6 times 10 to the minus 19 joules. And if you push an electron up a 1 volt hill and you let it go, that's how much energy it'll have at the bottom. And it'll be traveling at about 500,000 meters per second. Electrons are small and volts are big. Now, what looks like a hill to an electron? Well, basically anything that's charged, including other electrons. If you think of two electrons moving towards each other, imagine the field that one electron emits pushing on the other electron, trying to prevent them from being squeezed closer together. In the end, it's the same problem as rolling a ball up a hill. You're doing work. You're expending energy to push these two things together that don't want to be next to each other. And when you let go, when you stop holding on, they shoot back apart. If we try to imagine a hill shaped like a circuit, you could imagine a track with a variable height. The power supply is creating a large supply of electrons at one elevation and feeding them into the wire. The power supply is also getting rid of electrons at the other end of the wire and making sure that the electrons that have come through can't pile up. In between these two regions that are both controlled by the power supply, the electrons just roll down the track. This is what's happening in the wire. Hopefully in this example it makes sense that by making this path steeper, by increasing the potential difference between these two reservoirs controlled by the power supply, you can get more electrons to flow down the steeper slope. The trick is that this hill is formed by other electrons. Electrons repel each other. So if we wanted to model this more accurately, we could replace the track with a pile of electrons to get something like this. Now if we take this to the extreme and we replace the ping pong ball electrons with individual molecules of water that can slip past each other very easily, we get the water model that I'm going to be talking about in the next section. But there's one more aspect of voltage that I want to discuss, and that's exactly how electrons get pressurized. When you've got a battery using chemical reactions to cram more electrons into a wire, why does that store energy? And effectively increase the height of part of our marble track. If you want to get technical, and I do want to take a quick detour here because in this case it leads to some really pretty pictures, potential energy is an awful vague term. It's always kind of weird to say that kinetic energy just vanishes to be stored somewhere and that later it comes back into existence, when we actually do know where that energy goes. In this case, when you're cramming two electrons near each other, all of the energy that you're storing when you push them together as potential energy is actually stored in the space around the electrons, in the electric field around the electrons. It's really weird to imagine empty space containing energy. Like, there's no matter there. How could there be anything there? But if there is an electric field in that space, that electric field itself holds energy. Like, literally in units of energy per volume, you can express the strength of an electric field. Specifically, the amount of energy stored in an electric field is proportional to the square of the intensity of that electric field. And I normally wouldn't want to compute anything like that for a video, but in this case it's actually really important. Imagine a completely empty universe and place in that universe a single electron. The field that electron generates will store some energy. And if we had an electron in our empty universe in a different spot, the energy of its field would be stored in a physically different location. Now the real fun begins when we put two electrons in our otherwise empty universe. Their fields add together as vectors, then we calculate how much energy is in the resulting field by squaring it. In the space between the electrons, their fields point in opposite directions, actually canceling out and storing less energy. But everywhere farther away, the field from each electron actually adds together, and then there's more energy stored in the field, a lot more. As you get the electrons closer together, the total energy stored in the field, if you integrated all space, including the space around the electrons and the space between the electrons, increases. That's the energy that's ready to shoot the electrons apart again as soon as you stop holding on. So what does this have to do with electrons in a wire? Well, electrons like to roll downhill, but in order to create a hill, we need to rearrange some electrons. Imagine that we had a wire made of positively charged atomic nuclei surrounded by a sea of negatively charged mobile electrons. A 1 meter long wire like this one has about 5,000 coulombs worth of free mobile electrons in it. So if we take 1/5,000th of the free electrons that are in a wire and we start to push them towards one side of the wire, they're going to build up and they're going to form a hill. Now, if we push until that hill is exactly 1 volt tall, we will have used 1 joule of energy to build that hill. That's one of the ways that you can define a volt. It's sort of the pressure that you achieve after using 1 joule of energy to compress 1 coulomb of charge. Now, if we look at this hill that we've built, the hill's made of electrons, which means that the top of the hill has electrons that are on top of a hill. Also, at the other end of the wire, we've depleted the wire of electrons, just a tiny little bit. So the wire, being made of positive charges, now doesn't have enough to cancel those out. So we end up storing energy at both ends of the wire. We're storing energy over here because we've got too many negative charges that are too close together, and we were storing energy over here because we've got too many positive charges that are too close together. The more we compress the electrons at one end of the wire, the larger the difference in electron potential we've created, and the larger the Coulomb force is pushing any individual electron away from the concentrated bit towards the unconcentrated bit, and the faster they will push through any resistance. Now when we let go, when we release all of these electrons, all of the energy that we've stored in the field over here and all of the energy that we've stored in the field over here gets transformed into the kinetic energy of the electrons as they shoot down the wire trying to spread out. In actuality, they bounce around and end up dumping all of this energy into the metal as heat. But in the end, they will slosh back and forth until they have equilibrated their potential everywhere. The height of this hill, the voltage, the electrostatic potential is going to be flat when these electrons are done. And now we get to why the hydraulic analogy is so awesome, because that's exactly what's happening here. In a way, this trough of water is an analog computer, showing us a live plot of electron concentration in a wire versus distance, or at least a very good model of it. If you jam a bunch of electrons together, they store potential energy by crunching their electrostatic fields together. Just like when water molecules at high pressure, for example, at the bottom of this trough, get jammed closer together. Water isn't actually incompressible. Molecules do get slightly closer together, and they're slightly closer together over here than over here, until you let it spread out. I know it's not as pretty as the water models over on Practical Engineering, but I hope that it still gets the point across. The water trough is like the wire offering some resistance to flow. The water is like the mobile electrons that don't like to be compressed by voltage. And the pump over here on the floor is pumping a fixed volume of water per second, just like a constant current power supply. So let's recreate the experiment from the intro, where we ran a current through a wire. When the wire was connected directly across the supply, we got a smooth decrease in voltage from one end to the other. If I just turn on the pump and start moving water through the channel, we see the height of the water builds on one side. The voltage, potential energy of the water, drops as you go from one end to the other, and then the water is at a lower potential before being pumped back to the top. In this case, the potential energy is gravitational potential energy. This water is farther from the core of Earth than this water, but all the logic about water not wanting to be compressed works exactly for electrons if you're imagining one-dimensional current flowing down a wire. In the circuit, when I added an impediment to electron flow, a small resistor, the voltage in the same wire was pretty flat, but then stepped down and then was pretty flat again. If we recreate this in the water model by adding an impediment to flow, like this random piece of metal I found in the garage, we see that it obeys the exact same trend. The water level is flat, then it steps, then it's flat again. I hope that the water makes this intuitive for you. It certainly helps me. With the water, you just put a stopper in the way of the flow, so it's like, of course the water pools up behind the stopper. I like to think about electrons in the exact same way. This animation I showed in my last electricity video is probably my favorite animation I've ever made for the channel, for being an extremely direct picture in my head to video animation conversion. And we can see this principle at work. A battery pumps electrons around a loop of wire. Literally pumping one electron at a time with a chemical reaction is all a battery does. And those electrons the battery's pumping will then try to spread out and equilibrate everywhere through the wire, just like the water in the trough is trying to all reach the same height. If we make the resistor more or less resistive, or add more resistors, making a voltage divider of sorts, this is the sort of thing that you'd normally have to do math for. But in this case, the water height just responds accordingly, and it all ends up obeying Ohm's law, with the height of the water on both sides of each resistor being equal to the amount of water that's flowing through all of them, times some term that represents the resistance of each of these bits of metal that I'm shoving into the water channel to slow down the flow. It's also important to keep in mind that voltages are always relative in circuits, and the water model is no different. In the intro example, I had the negative clip of the multimeter attached to one side of the power supply for every measurement. A voltmeter like this only measures the difference in voltage between two leads. So when I say this point is at 1 volt, I really mean the potential at this point is 1 volt higher than the potential at this point. And when I say the potential here is about 0 volts, I really mean that this point and this point are at approximately the same potential. If you somehow charged this entire wire and the absolute voltage was way up here, it just doesn't matter because the electrons can't leave the wire. All they care about is the height of the hill they can see. In the water model, if you want to use height as a voltage equivalent, you need to choose a reference location. If I choose this as a reference point, we could say this whole area is at 0 height, and this area is at 2 centimeters height. Or we could drop our reference on the other side, and this area is at 0 height, and this area is at -2 centimeters height. The absolute position really doesn't matter. When you want to look at the voltage drop across a certain component, you only need to look at the difference in potential on both sides of that component. As an example, when you put a bunch of resistors in series like this, it's called a resistive divider because it takes the total voltage drop across the entire circuit and divides it into chunks based on the relative strength of each resistor. If you tried to figure out what was going to happen in this situation using math, arithmetically with Ohm's law, what you'd end up calculating is the difference in potential, the difference in voltage on both sides of each of these resistors. In practice, this is normally known as the voltage drop across any given component. In the plain wire versus wire with resistor example from the beginning of the video, there was another cool thing, or maybe hot thing, that I glossed over: power dissipation. In the case where we have voltage dropping smoothly across the whole wire, we can look at any little bit of that wire, say the voltage drop times the current is the power, and see the amount of power dissipated in this bit of the wire is going to be the same amount of power that's dissipated in this bit of the wire and this bit of the wire. It's basically the same everywhere, making the whole thing hot. In the case with the resistor, the voltage in the wire is basically flat. So if you take the current in the wire times a voltage drop of basically 0, you get basically 0 power dissipated. There's hardly any heat being dumped into this wire. But at the resistor, the voltage drop is significant, so I times V equals a lot of power. Just like friction between two surfaces, resistance generates heat. So when our electrons have to force their way through a big resistance and undergo a large change in potential right here, all in the same spot, all of that energy gets dumped into the system as heat, all in one place. It's the difference between a meandering creek that runs on for miles and a waterfall that accounts for the same elevation drop over a much shorter distance. In a more technical sense, the electrons over here were too bunched up, and the electrons over here were too spread out, which ends up causing atomic nuclei to be too bunched up. In both cases, a lot of extra energy was being stored in the electric field. As electrons from the too dense region travel through the resistor to the electron deficient region, for a brief moment, they are at exactly the correct spacing. So the energy that was once stored in a deformation of the electric field is now in the kinetic energy of the electron. This is the fastest it'll ever be going. Now, since electrons passing through copper run into something about every 40 nanometers, they will almost immediately collide with and dump this extra energy into some poor unsuspecting atomic nucleus. And all of that coordinated kinetic energy, as all the electrons are trying to zoom down the wire at once, will quickly become incoherent vibrations as the whole lattice starts shaking, aka heat. At the end of the day, potential energy stored in the electric field and caused by forcing similarly charged objects too close together moved from the power supply towards the load. But the nature of the load determines how that energy is distributed, and this all can be extremely accurately represented by water flowing through a trough. I don't think it's going to come through on thermal camera, but if you really wanted to, you could calculate how much energy is being dissipated by the water at this junction. Physics is just crazy enough that all of the units still work. For electricity, we take the equation power equals current times voltage, but since current is now water flow and voltage is now height of water, we can type something like this into Wolfram Alpha and actually calculate how many watts of energy are being dissipated as heat in this junction. Energy that's flowing from the pump in both directions, meeting at this point and warming up the water and the trough. When I first learned about Ohm's law and resistive dividers in a textbook, I could do the math, but I didn't really understand it. I didn't understand why the voltages were plateauy and how they could separate between resistors and stuff like that, until I really thought about how electrons were flowing and how electrons could sort of pool up behind large resistances. In order to make sense of this, I needed to imagine electrons flowing through a wire the same way that water flows down a river, maybe with multiple dams in that river causing the water to pool up, because that's literally what the electrons are doing. I think this is a wonderfully intuitive model because the microscopic motions that lead to electrons being compressed and pooled up are very complex. But if you isolate it to a one-dimensional case, it's the exact same thing that happens with water. And with water, you can just look at it and you can read the voltage by looking at the height of the water. It happens so much slower than electricity, and it happens on a tangible human scale. I hope that by this point in the video, you think Ohm's law makes a bit more sense. If you put a larger impediment to flow, you're going to pool up the electrons more on one side, which leads to a higher voltage. These are two completely different physical systems that end up obeying almost exactly the same rules and for largely the same underlying reasons. And for all but the most esoteric of circuits, it's really all you need to get started in electronics. My favorite part of this metaphor of sorts is how it can model dynamic systems. It's really fun to look at all these steady state models and say that Ohm's law is satisfied by the water model. But what happens when you flip a switch? I'm going to pull this blocker out of the water stream and effectively flip a switch, at which point the circuit will see a wire with a resistor in the middle. Now before I do that, think about what's going to happen. The water is going to move this way, and then what? Do you have an idea in your head? Okay, here it is. There's a wave of water moving towards the resistor. Some of the wave passes through, and some of the wave bounces back. And then after a few reflections, all the sloshing settles out. Now it took me a long time to figure out how to do this with electrons, because the waves of electric current move at almost the speed of light. But here we go. The wave is released, it travels down the wire, some is reflected off the resistor, and some goes past the resistor. And after a minute, or in this case, after about 400 nanoseconds, it settles out and obeys Ohm's law. I'm not going to go into how I made this measurement at all today, because that's a topic for the next video, but I thought it was really cool and I thought it was relevant to this, to show that electrons in a wire really do slosh around just like water in a trough. Stay tuned for that one. But for the remainder of this video, I'm going to rapid fire some clarifications that I know will otherwise, and will probably anyway, produce many comments. I want to defend the point that the water model can handle pretty much everything. I've received a lot of comments saying that electricity isn't electron flow, that either the electrons don't really move or that charge somehow flows without electrons flowing with it. But electrons really do move. When I said a certain number of electrons were going in and out of the power supply when talking about current, I wasn't making that up. Even in the case of alternating current, 60 hertz that comes out of your wall is so unimaginably slow that for resistive circuits like the one that I was talking about here, you can basically just solve DC flow in one direction, and then a half a period of the sine wave later, you can solve a separate equation for DC flow in the other direction. All of that, the switch just flipped sloshing thing that might occur when you have DC flowing one way and then your polarity flips and you suddenly have DC flowing the other way. All of that sloshing is over with in a span of nanoseconds. And the AC that's coming out of your wall only flips polarity a few tens of times per second. So, I mean, it's an eternity by the scale of electrons and photons. When you have a lot of electrons jammed together, that's actually a very low voltage, or a high negative voltage, depending on where you're indexing from. That's because electrons are said to be negatively charged particles, while protons in atomic nuclei, the thing that doesn't move, is said to have a positive charge. Unfortunately, this means that conventional current flowing from positive to negative is actually in the opposite direction that electrons move through wires or any electrical device. This is such a famous blunder that it's actually the topic of one of my favorite XKCDs. And you may have noticed that I very intentionally didn't talk about it in the bulk of this video. And that's because it really doesn't matter. If you want, you can imagine that the water trough is filled with some magical, positively charged thing that can move, and that we're actually looking at conventional current. Or you can just flip the labels. It's just a really annoying thing to have to keep in mind. Positive charge carriers don't really exist, unless, of course, you're talking about in a metallic N-type conductor, like I've been describing, any metal that you've ever heard of, you could imagine an electron as a particle moving a long distance through that metal unobstructed. Electric charge is moving in this case because you have a particle, a charged particle that is moving a long distance and carrying its charge with it. But in some materials, as I'm sure commenters will point out, the energy levels and the Pauli exclusion principle, not letting electrons run into each other, basically creates a traffic jam where very few electrons are able to move. Imagine you have a grid of electrons, but they're all too packed in. Now, if you create a hole in this structure, you can get electrons to move, but only a tiny bit. If you want to move charge a long distance, you need to move a large number of individual electrons. So it's more convenient to calculate what happens to this void. If you say the void moved from here to here, that's a lot easier than mathematically describing what happened to each of these electrons during that period, especially when almost all of them were locked in place for most of the time. This gets weird because a lot of materials macroscopically behave as though they had positively charged mobile particles, but they don't. Holes aren't real. At the end of the day, it's still electrons that are moving. It's just that you have a lot of electrons that each move a short distance instead of having a single electron that moves a long distance. The depiction of balls bouncing off a fixed lattice is a great way to think about resistance as a classical thing. But in reality, the electrons that are ricocheting through this structure aren't billiard balls, or in this case, ping pong balls. They're probabilistic waves, and they can bounce off of atomic nuclei, they can bounce off of each other, they can bounce off of vibrations of the lattice, or they can bounce off of pretty much any crystalline defect. An electron can even bounce off of a vacancy where there's an atom missing from the crystal. I do not have the skill or the spare front teeth to film this for real, but imagine someone running or parkouring across like a series of posts in the ground. If the posts are evenly spaced, they get into a good stride, but if a single post is missing or even out of place, they'll miss and crash. The same thing can happen with an electron traversing a crystal. It's just the electron normally doesn't have to go to the hospital after. It just gets up and starts running across the grid of posts in a different direction. The water trough model handles the capacitance of the wire itself really well, which is, I think, something that's pretty rare in electrical analog models. Capacitance is actually defined as a charge per voltage. It's literally how many electrons do you need to add to a thing in order to raise the voltage, raise the water level by a certain amount. In reality, this number is all over the place and varies significantly down the length of wire depending on what's around it. In the water trough model, the capacitance isn't constant everywhere either. Near the ends where the tube comes in, the channel is actually thicker. The capacitance is higher here, and the amount of water or charge per length of trough is higher, but the water level, the voltage, is the same. In my mind, this is a perfect analog because capacitance, the amount of water that you have to flow into the wire to change its voltage, matters when you're trying to change the voltage of the wire. But in DC, once the whole thing reaches steady state, it just doesn't matter, which is why this particular model works really well for things like Ohm's law, where we're looking at steady state, how the voltages settle out after a long period of time. The last point I want to make about these water models is scale. The water in this trough is very intentionally only a few inches deep because if I poured any more water in, the bottom started to leak. I did a really terrible job of caulking it. Well, it looks like I'm done for the evening again because But imagine that if the water level below this was twice as deep, all the same physics would apply. It's just that if you were to flip a switch and let the water slosh flat, you wouldn't need the water to move quite as far. In order for this to become this, you don't actually take this water and put it over here. All of the water just sort of sloshes in a circle. And if you have a lot more water down below, any given molecule doesn't have to move very far as the surface settles out. In order for a 2 centimeter difference in water to be equivalent to a volt, and for the amount of water to be directly equivalent to the number of electrons in a wire, again, making some very broad assumptions about capacitance, this trough could be maybe 7 billion miles deep. All the underlying physics works in exactly the same way, but the motions of the electrons are slowed way down because there are just so many of them. When we play with electricity in circuits, we are really only splashing with waves on top of a very deep ocean. Thanks for watching, and subscribe if you want to see the electricity waves video because I'm really excited about it.